Hi all, there was a lot of comments on a recent video when I played the apparent engine abuser. Let's see how he's getting on the ICC, but before we do, let's have a quick review of a formal computer chess paper. Now this was done by someone called Graham Owen, who was studying, I think, for a master's degree, and I had the pleasure of working alongside him when I was working for Dexian within IT at Dexian. Now he did this paper on search algorithms and game playing. Now I suggest we look at this paper from the point of view of how to beat engines. Anything said, we'll try and work out the implications for beating engines. So basically, in the field of search algorithms, Graham indicates there's a type of search known as adversary search. So you've got an adversary, so it's applicable to game playing. Adversary search can be used in games that have the following characteristics: a two-person game in which players have alternate moves. Games of perfect information. So in which each player's alternate moves requires thinking about which move to make, and also requires thinking about how your opponent will move in response, how you will move, how you will respond to their response, and so on. So that sounds like chess. A game of perfect information, in one which all the relevant information is available to the players, yes. Noughts and crosses also ticks that box, an example of a game of perfect information. Same with drafts, Go, but computers haven't done very well in Go, and chess. While poker is not, as presumably each player does not know what cards the other players are holding. Okay. It's interesting Graham actually didn't mention, the lack of success in Go. Okay. But chess is an example of adversary search that has many solutions: a win for white, a win for black, or a draw. But the computational cost of finding a solution is prohibitive. So this essay shows how the Minimax search procedure and its improvement in the form of alpha beta, these are Greek letters, alpha and beta procedure, used in chess playing computers. It also covers the heuristics, which are like rules of thumb, used in guiding the search, and discusses some of the ways, the problems that the Minimax procedure, and some of the ways which have been used to try and overcome some of the problems. So there's this idea of Minimax. But Graham addresses this issue of the combinatorial explosion. So in chess, the average branching factor, the number of legal moves from any position, is approximately 35. To search for a tree of average branching, factor B to depth D, so D for depth, B for branching, requires that B to D positions be generated and evaluated. Okay, a chess playing program wishing to play at an acceptable level needs to search to a depth of 4 plies, which means examining around 1.5 million positions each move. A search to a depth of 6 plies requires the generation and evaluation around 2 billion nodes. So this is implying one weakness already of chess engines, that if they don't get the depth, then they're out of their depth. It's like the horizon effect. So in the early engines, that was apparent. You could offer a pawn, get their queen over on the queen side, then mate them. But because they came deeper and deeper, they stopped falling for cheap tricks and decoys like that. So the combinatory explosion means that any program wishing to play chess at anything above novice level has to apply techniques to tame the growth in the size of the search space. So just applying more computing power to the problem does not help. The number of legal positions in chess is estimated to be 10 to the 40, and the number of different legal games that can be played is estimated to be 10 to the 120. Most chess playing programs rely on a combination of two techniques to improve play: the use of the alpha-beta search algorithm and a good heuristic to classify positions. So Graham's pointing to the evaluation function here, the good heuristic to classify positions. So heuristics. As it is impossible in a game of chess to perform an exhaustive search on a position, a heuristic, so he's talking about an evaluation function, needs to be applied to guide the search towards the desired goal. The heuristic applied in chess playing programs is known as the static evaluation function. The purpose of this function is to provide an estimated measure of the winning chances of either side based on the features of the position and return a score for that position. So this is the evaluation function, which we see, in engines. The evaluation function often takes the form of a weighted linear function. So a weighted linear function, so it looks like this. Okay, where f is a feature of a particular position, and W is the weight. So one feature could be pawn structure, another could be king safety, and you apply different weights to the different features. So by taking F as the number of pieces in the position and W as a value associated with each piece, we can build up a simple heuristic based on the material value of the pieces on the board. But I thought you could apply this to other things. I wasn't just thinking material there. But anyway, as an example, the GNU chess program assigns the following values to pieces. So white pawn 100, black pawn minus 100, white knight 350, bishop 330, rook 520. Okay, at the start of the game, the valuation position will produce a score of 0. If the pieces are lost, the score will move to be positive for an advantage to white and negative for an advantage to black. So the king effectively has an infinite value because capturing the king wins the game. So the basic heuristic which is talked about here is just raw material with a weighting, but I think you can have lots of other features added to the evaluation function. The static evaluation function can be made as sophisticated as we like by adding positional features such as good pawn structure or greater piece mobility or any other factors that seem relevant. So however, the trade-off between the time taken to do a search and the time taken to apply the heuristic must always be considered. So we can apply that same thing for positional features, not just material, this weighted evaluation function. So you've got weighting and you've got a feature 1, feature 2, feature 3. The static evaluation function, okay, the Minimax algorithm, the diagram below shows the first 3 simplified applies of the search space for a position in the game of chess. The evaluation function has been applied to the nodes at the edge of the tree to give the values shown. Okay, so we've got an evaluation function here, and so white, then black, white, and then the scores. So you get these scores, and basically the scores from the leaf nodes. So this score has 16, this has -5. So that some lines of play result in white winning a pawn. Those scores are running 100 because the pawn was about 100. So white's winning a pawn here, maybe more than a pawn here. One gains the knight, and the remaining moves result in slight positional advantages for white or for black. So 28, 54, 96. These are slight positional advantages. If the computer is playing white, what move is the correct one to select? Well, Minimax. So I assume that the maximum is 102 and the minimum is -5. But here the maximum is 187 and the minimum is -3. So I guess this move looks stronger. Okay, if the computer plays into the right hand side of the tree, hoping to gain a knight, its opponent will surely play to prevent this and play into the left branch to apply 1. If we assume perfect play from the computer's opponent, we can see that the general rule is that each player will attempt to maximize the gain from each position while allowing only the minimum gain for the opponent at the next move. So this is the basis of Minimax. So the Minimax algorithm assigns one player as the maximizer and the other player as the minimizer. So at each ply, the maximum or minimum score returned from all the nodes is backed up to the node above. This process is followed recursively until the root node is assigned the backed up score of the target node. So these results all get backed up: 102, 102, 102, 28, 28, 28. So that shows how the maximum score from each of the subtrees at ply 3 has been backed up to ply 2. The minimum score from that ply is backed up to ply 1. Finally, the maximum score 102 assigned to the root node. So that root node 102, see, it got that score from over here. That 102 was backed up down there. So this shows that the next move to make will gain white an advantage of a pawn. Okay. So a Minimax implementation. The following code is an efficient implementation of a Minimax search algorithm written as an Eiffel function. Instead of writing separate functions for the maximizer and minimizer, the code takes advantage of the fact that the positive score for one player is equivalent to the same negative score for the opposing player. The function can then call itself recursively as it searches down the tree, returning the backed up score from the lower plies. The minimizing and maximizing at alternate plies is achieved by negating the result returned from the previous recursion. So this method of implementing the Minimax algorithm is often called Negamax. The class position is a representation of ball position. The function evaluates the position as a parameter and returns a score for the static evaluation of that position. The class successors is created with reference to position as a parameter to its creation procedure, then generates all the legal successor positions which can be accessed by the procedure next. A Boolean value empty, Boolean is like true or false, is set to true when all the successful positions have been returned. So the recursion is stopped when the value of the depth falls to 0 and the function applies the static evaluation function to the leaf node. So here it is in code. See, when it reaches the root, depth 0, the result's evaluated. Otherwise, it's kind of okay. It's getting a bit technical now. But here's the recursive function. So it loops basically position like this. If it's best, if the score is better than best, then best becomes the score. So the code itself only provides the backed up value of the target node. Additional code will be needed to identify the move selected to play by the algorithm. Okay, so we've got this. The first 3 nodes have been evaluated and the maximizer of 102 has been backed up to the ply above. The 4th node evaluates to a value of 187. Do we have to evaluate the 5th node? We can see that the backed up value of the branch is going to be bigger than 187. But the maximizer already has a choice to play the left hand branch with a value of 102. As we already know, the minimizer will never play into this line. So we do not need to spend any more time evaluating the remaining nodes on this branch. So the process of discarding branches that we do not need to evaluate is known as pruning, and the result of pruning is a cutoff. So basically, so because it was 187, there's no point looking at that from the opponent's point of view, I think, because 102 was already achieved, already a better choice there, 102. So the alpha beta search algorithm is based on maintaining 2 values, alpha and beta. So initially set to minus infinity and plus infinity respectively, alpha representing the value of the best path so far for the maximizer and beta for the value of the best path for the minimizer. So the alpha beta search updates the values of alpha and beta as it goes along, with the maximizing nodes only able to increase the value of alpha and minimizing nodes only able to decrease the value of beta. This creates a window in which it gets narrower as the values of alpha and beta approach each other. Any branches of the tree that have values that fall outside of the range are identified as being worse than the current best choice and immediately pruned. So this is the basis for alpha beta pruning, which I think all modern chess engines are making use of. So they can prune. So basically, so we see here in the part of the search space shown above, the left hand side of the tree has been evaluated and a value of 102 has been backed up to node B. So node B, we see a backing up of 102. The right hand side of the tree is now searched. Node F has been evaluated to minus 28. What can we say about node G? Since black is the minimizer, we know that the backed up value at node E is minus 28, and this is less than the value of 102 at node B. We also know that white will not play into this line and node G can be cut off. So node G, we can just cut it off. A situation such as this where the pruned node is more than one ply below the reason for the pruning is typically referred to as deep alpha beta pruning and occurs only in searches in depths of 4 plies or more. So here's an alpha beta implementation. So basically, okay, I'll give you the link to this technical paper. And I think I'm falling asleep. All of you have probably fallen asleep by now, but I'm going to give you the link to this paper. So it's everything you wanted to know about alpha beta pruning, but we're too scared to ask anyone. So basically, there are some problems. Some chess players doubt whether a single number can be used to classify a position as better or worse than another. Problem in Minimax and its alpha beta refinement is the assumption the opponent will always make the best possible move. So in a winning position, the assumption appears valid, but if the opponent makes a worse move than expected, and it only hastens his demise. However, there are situations when defending a losing position where this assumption can be harmful, and that's true. I've found in my own over-the-board games that sometimes I've swindled opponents because I've played dodgy moves, but they worked out. But if I was an engine, of course, trying to play the best moves, that would never have happened. So it gives an example here that a program, after doing an extensive search, has found a forcing line for its opponent and results in its defeat. The computer's next move will be made on that assumption, and on the assumption that its opponent has also discovered the forcing line, so its own strength is being used against it. So imagine there's also a similar but slightly worse move that the program can make, which is in effect a bluff, which will try and draw attention away from the best player. A human may try the bluff in a losing position in the hope that the opponent has not seen the best reply, but a computer using a Minimax search cannot. So that's funny. That's quite an amusing thing to bear in mind. Okay. There's also the philosophical question of how a computer using a brute force look-ahead program appears to be able to play chess at the very highest level. Certainly human chess players, even grandmasters, cannot look as far ahead into the game as a computer. It appears that humans play chess mainly with a combination of experience, pattern recognition and intuition, quite unlike a computer. So the horizon effect, this is a major issue about search depth. So if it's only looking at 6 plies, discovers it's going to lose its queen in ply 5, it will naturally discard the line in favour of a better one, which the queen's not lost. However, it could be that the resulting sequence of moves is just delaying the inevitable loss of the queen by introducing some delaying tactics. The queen will still be lost, but it's been delayed so that it does not appear in the tree. So the inevitable bad event has been pushed over the horizon. There is no general solution to this problem. I think just the bigger depth actually is a solution to that problem of horizon, looking deeper. Okay. So basically, iterative deepening. If we're looking in best move order, there's iterative deepening. Rather than searching to a fixed depth, the game tree is first searched to a depth of 1 ply and a static evaluation function applied to a result of each of the possible moves. So this orders the moves that a best likely candidate is examined first on research. This time to a depth of 2 plies, and then it can be applied to 3 plies, 4 plies, so on. So the time spent in evaluating the nodes at shallower levels is more than repaid because the move ordering at each ply ensures near optimal alpha beta pruning. So we're trying to get optimal alpha beta pruning there. So it's called iterative deepening. Quiescent search. So the evaluation function is used to assign the score to a position that is only meaningful if the position being searched is relatively quiet or quiescent. An example of a tactical or non-quiescent position would be one which an exchange of pieces is in progress. A position may give a high score when the opponent's piece is captured, but this is false because the apparent advantage is lost in the next move. Quiescent search says that the lines of play that involve an exchange of pieces should be followed until a quiet position is reached, ensuring that the evaluation function is only applied to positions that are quiescent. We can detect tactical portions of the search space, because these are characterized by rapidly changing values of the heuristic function. Singular extension, so you follow lines of play beyond the normal search in cases where there is one option that is vastly superior to the best. In chess terms, a forced move. Oh, this is like docking computer stuff. When we talked about this, I talked about docking computer for forcing moves. As this move is forced, so this is like applying singular extensions really. The effective branching factor is smaller, and a search to a depth of a few more plies becomes computationally practical. So they were first introduced by chip test. So quiescent search and singular extensions are both examples of secondary search. Conclusions. Chess playing computers using techniques described in this essay are now playing at grandmaster level, believe it or not. Some observers see the time approaching when a computer will be able to beat any human player at chess, whilst others say human skill and ingenuity will always find a way to beat the machine. In May this year, when this paper was written, the world champion Kasparov will play a match against Deeper Blue, IBM's latest supercomputer. Kasparov, regarded as the best player in history, won his last match against Deep Blue, but lost a game in the process. Can Deeper Blue beat Kasparov this time round and prove itself better than any human player? Yes, unfortunately, it did. So, I hope you enjoyed that. Many thanks to Graham Owen for allowing the author to use this fine paper. So that was in my old Barnet Chess Club website. For those that wanted to know, I'm going to give a link to this. Thought we'd go for it together. Good revision for me. Given there's some interest in beating engines, it's good to know how they tick. Okay, comments or questions on YouTube? Thanks so much.